Good morning, everyone. Welcome to the February SC Fraunhofer USA Alliance webinar. We're happy to see you this morning. As usual, we will have a presentation from a Fraunhofer Center. We're always in these webinars, of course, trying to communicate some of the capabilities that exist within the Fraunhofer network, whether they are in the US or they are in Germany. Today we have a center from Germany presenting. Very excited to have two speakers from that center with us. Of course, the objective here is to highlight capabilities that may be of interest to your organizations. And if they are of interest, you can always reach out to me or Dr. Marcel Schaefer after this event, and we can get you in touch and make some connections. Please remember that we have matching dollar for dollar contributions on behalf of the Department of Commerce that we can contribute to projects if you would like to have us help you set up a collaborative team. Between Fraunhofer, one of our state universities, and we can try to match your funding for those. So with that, I would just ask you to note the comment here about please remain muted until we are finished with the presentation. There'll be plenty of time for questions and answers in the chat session afterwards. Marcel and I will manage that. And I'll turn it over to Marcel for introductions to our speakers. Thank you.
Thank you, Suzanne. Hello, good morning or good afternoon as well from my side. Thanks everyone for joining this month's episode of our Fraunhofer webinar series. Today's topic, titled Lightweight Production Technologies. So our speakers will highlight innovation projects for the automated series production of lightweight components, focusing on high performance materials. So you can look forward to insights and use cases provided by our two speakers representing Fraunhofer IPT in Aachen, Germany. For the record, we're already pursuing an alliance project with other colleagues from Fraunhofer IPT. So this is a wonderful example. This is about a different topic, but the project is a wonderful example of how companies in South Carolina can get world-leading experts from all over the world, Aachen, Germany, for a neat innovation project for the better of South Carolina here, and they only pay half of the budget because of our alignment with the Department of Commerce. So today we have two speakers tag teaming, Malena Schulz and Florian Schmidt. Malena Schulz is group lead of the fiber reinforced plastics groups at Fraunhofer IPT. In a role as a researcher and group leader, she encourages novel production technologies for automated production of composites and the integration of industrial Internet of Things. So she studied mechanical engineering at IIot Zurich and RWTH Aachen University with an emphasis on FEA, finite element analysis, and production systems of fiber reinforced plastics. Just for the record, these are kind of two of the best universities in Europe that you can find. So we have real experts here. Florian Schmidt also belongs to Fraunhofer IPT's research staff since October 2015. Since July 2018, he leads the group Laser System Technology. His research focus is on developing customized laser heating systems for efficient processing of high performance materials for a variety of different applications. He also studied mechanical production engineering also at RWTH Aachen University with an emphasis on laser technology and production machines. So I'm expecting to see some fancy laser applications today. The three of us have something in common. We chose the Fraunhofer career road so far. We all started our work with Fraunhofer already as a student. Maybe did the bachelor's thesis, maybe the master's thesis, and then becoming full-time researchers at Fraunhofer. So we breathe this. As always, stay muted, hold your thoughts, put them in the chat. We'll get to them after the presentation. And now, Florian, Malena, the stage is yours. Kick it off. Thank you.
All right, so thanks for having us.
Yeah, good morning, everyone. I'm going to start the presentation. I have to get the controls and then I'm going to start. Somehow it doesn't work anymore. But Flo, you can just
I can do it
slide
for
the
you.
stars.
Sure.
Yes, thank you very much. So a warm welcome from our side, from Fraunhofer IPT. Yeah, good morning to the USA. Good afternoon to Aachen here in Western Germany. Today we're going to show you how to produce composite fan blades or to process high-strength steels for lightweight structures. And we provide you with solutions how to do that in an automated and upscaled way, because we are system builders, or I like to say we're actually doing that what mechanical engineering is called in Germany, because mechanical engineering is actually called building machines. So the word Maschinenbauer, and that's what we do here in our department. And we do that on the one hand for composites, and on the other hand for high strength steels, where we show you some application and use cases. But let's start with our system technology. Me as a leader in the composite groups, we're building such machines, which you can see here in this animated video, where we stack tape by tape. That's how the composite material is called here, in order to create a near net shape composite parts. And the new thing here, what we're focusing on, is especially to automate that. So it's a lot about how to upscale composite production, which is kind of actually very manual based production technology, and how to use novel methodologies like digital twinning, etc., to increase the acceptance in industry, and also to provide also the requested productivity, for example, in the automotive sector, in which more and more composite become apparent, but it still faces some challenges, especially regarding costs. And the focus we have here in our departments, especially how to customize the heating source in order to gain these kind of produced quality and near net shape parts. I hand over to Flo back again, who will focus.
Okay, yeah. Thanks. Yeah, maybe your thought initially, how does composite production and laser systems together? But actually, as you might have already guessed from this little video, our processes are all about applying energy to the workpiece in a very controlled and precise way, in order to allow for the product quality that we want. And so in our group, we are more focusing on high strength steels as another lightweight material, especially in automotive industry. And one example is that we are researching how to bring these technologies into the processes that already are there and that are already very productive. And what you see now is that we have different heating technologies. So we are not only focused about laser technology, but we rather look which technology suits the use case best. And so this, for example, is a continuous production of sheet metal parts. And we've integrated different heating technologies into the progressive die tool in the press. And so we are able to manipulate the material locally and within the cycle time of this highly productive process. For example, we also apply induction heating technology, or also electrical resistance heating. And this is really a case-by-case assessment, which one of these technologies is best suited for the application at hand. All right, so I will give you a short introduction of our Fraunhofer Center in Aachen. Yeah, so we are located at a little bit outside of the city of Aachen. It's in Western Germany, very close to the Netherlands, if you know that geography a little bit. And the campus that you see on the slide is a very fast growing echo chamber, let's say, for university research and applied research, but also for different companies from industry coming to this location and conducting research with us at the same spot. So Aachen is quite a big research Center for Production Technology, and we are proud to host 3 Fraunhofer centers at one location very close to each other, actually only a few minutes away from each other. Just very briefly, maybe you've heard some of these 4 names. So yeah, production technology is a quite interdisciplinary field. It's not only about a machine, it's not only about a process. It's about how these two interplay, and it's also about how the quality of the process and of the machine is assessed. And finally, everything needs to be economical in the end. So that's why also technology management is one focus of our center. And these are the 4 professors that we have that lead the 4 departments. And well, yeah, we are obviously from production machines, but we always have a good collaboration with our colleagues from the other departments. So what are the current trends in automated lightweight production? So definitely we are facing the question of how the mobility of the future will look like. Yeah, just some buzzwords. We certainly have new energy sources like electromobility, or also hydrogen based mobility, and these have different implications for the structures of, let's say, vehicles, for example, and also then the production technologies that are used to build these structures. And on the other hand, we are also, yeah, of course, focusing on doing what we do more efficiently and more environmentally friendly. So, for example, recycling technologies or energy efficient processing, as you will see in the following slides, are big drivers of what we do. So just to give you a quick framework about what lightweight means. So lightweight can have different dimensions, and we are mainly today focusing on different materials. So having materials with lightweight properties, but there is of course also lightweight design, like you've seen in 3D printing with optimized topologies, or different concepts, how to build new parts in a new way, or to integrate functions into lightweight parts. But yeah, as I said, we are mainly focusing on materials and of course the production technologies used to shape these materials. Well, so what's the technological driver of different lightweight materials? So yeah, as you've already seen, we will focus on high strength steels and composites, especially carbon fiber reinforced plastics. And you already see that these have a very good component weight ratio compared to conventional steel materials. So high strength steels, due to the higher strength, we can use thinner structures. So you can approximately save 20% of the weight for a comparable component. And with carbon fiber, the potential is even bigger. So you could halve the weight of your component. But on the other hand, it comes at a cost, let's say, and that is basically also what we are targeting. So we are trying to develop new technologies that make the application of these new materials competitive. So trying to cut down these costs, especially if you look at the carbon fiber, there's a huge cost disadvantage that needs to be justified. And so that's our mission to reduce this, to bring these materials into application. On the other hand, based on the global trends that you just saw, the composite market, the lightweight market is steadily growing, having surpassed 100 billion euros a few years ago, and especially the high strength steels are increasingly used, especially in automotive industries. I think composites are also growing, but it's still a kind of a niche market that needs to find its way into mass production. One example could be if you look at the current vehicle, or this is McKinsey data about the projected material mix in a vehicle of the future. You can see that there is increasingly more of these lightweight materials in a product, in a car, let's say, and this as you might imagine, makes production technology a lot more complicated than if you just have 50% of very easy to shape steels, for example. So this is what drives our research. Trying to bridge the gap to what I'm showing you about our particular research. I brought you one example about press hardening. You might have heard of that for sure. So this is about heating press hardening steels in a furnace and then putting them into a tool, shaping them and giving them specialized hardness and strength properties. And so this is the trend that we are seeing. So it's not a monolithic component made from one material processed in a very easy way, but it's getting more and more complex, and you even have localized material properties, for example, in a B pillar or in other structural components in a car. So this gives you certainly a lot of advantages, but on the other hand, you have higher energy demands. You need to have your handling systems in place, and also it has different downstream implications for example, if you want to cut these things in further processing steps, or if you want to integrate functions, it gets difficult if you increase the strength of the materials. So that's why we use thermal assisted sheet metal working for high strength steels. And the motivation is really to enable the material to or enable the current processes like cutting or forming to give us better results with these high strength materials. And for example, if we look at shearing, we are able to heat up the materials and increase the clear cut ratio. So you see there is less fracture, there's better quality of the cut. And also for forming, higher expansion ratios or higher forming ratios can be achieved by applying heat in a very precise way by different heating technologies. So if you like, later on you can have a look at these videos again. This is some of our technology videos, but basically we like I said, we always look for which technology is best suited for example, how complex your heating should be, how thick the material is, and how large of an area you want to heat up. So now I brought you some product examples that are from real world projects, either research projects or sometimes also bilateral projects. And this should show you what different products could be made with these technologies. So this is an example I really like. This is about function integration. So on the right, you see the component without any heating. So you see there is the fracturing of the material, but once it's heated up, the formability is increased by up to 130%. And then you're even able to add a thread to this component and use that for fastening. And so for the customer, it's really a good way to reduce the number of parts in an assembly. And it requires obviously less handling and storage. And this is done with one of our laser heating systems. Another example could be that we increase the formability by heating and also apply some tailored hardening. So again, this is a flange structure that you could use in this case to do some mounting of different parts. And in this case, it's not only possible to increase the formability, but also to locally have a heat treatment at this structure, for example, to make it more wear resistant. And the good thing is that by doing that very locally, the energy costs or the energy expenditure is greatly reduced. And on the other hand, it's less expensive than having high strength steels to begin with, if you only want to achieve a certain property at a very limited area of your part. Another example would be if you again, if you want to have localized hardness properties. This is like the little gear wheel that we had at the introduction slide. And in this case, again, it's possible to very locally and in a precise way to have the hardness of the component modified, and during this, in the same step, when it's being shared in the tool. You see where this is going. Basically, you can improve almost any process that you might imagine, from metal forming or cutting with heating. In this case, it's bending, and the benefit for the component or the customer would be that you can have more design freedom, because you can do these very sharp bends with this very high strength materials with 1,500 megapascal yield strength. And maybe another thing that is quite common now, obviously, is the digitalization of production. And with these parts that you have seen, it's always a challenge, because they are usually bulk parts. So it's very hard to get a quality data storage based on individual parts. But this is actually crucial if you want to produce efficiently and have safety critical parts. And so we developed a method that is able to do marking in the press, in the tool, so that you have 100% traceability, and then later on can take your quality data, can take your process forces from the tool, for example, and store that with the part. And you're always able to go back and see if something has gone wrong or if not. Finally, maybe that also illustrates a little bit how Fraunhofer is working, how we work. We always try to get the most up-to-date equipment at our workshops, so that we are able to, in an R&D environment, still use equipment that is relevant to industry. And so this is our servo press line that can do up to 200 tons of press force, and stroke rates of up to 120 strokes per minute. And so then we are able to use customer tools, integrate heating technologies, for example, and make evaluation of performance very realistically. So, and this is a topic that maybe bridges also the gap to Malena now. So we thought about, we are always processing sheet metals very productively. So why not like do a technology transfer to composites? And as you saw, we are getting more and more composite parts in vehicles, for example. So this is like a door panel where all the components are fixed behind the nice interior of your door, and these are increasingly made from composites. And the hardest part actually is trimming these components because of the abrasiveness of carbon fibers. You need to find a technology that is, on the one hand, quick, but also enables good cut quality and doesn't exhibit too much wear, which is really critical. And so that is why we have built up in a research project progressive tool for a demonstrator geometry. So this is glass fiber reinforced polymer tape that could be used, for example, as a reinforcement in injection molding. And these are processed in a very quick way, as my colleague Tobias is showing you now. So you see, we like in metal manufacturing, we come from a composite coil, and then the material is fed through the tool. And these features are created by, for example, shearing. And you're going to see, maybe you're going to learn a little bit German now. You're going to see that we can achieve really high productivity with this kind of method. So we are here ramping up the stroke rate up to 120 per minute. And so this is a new level of production of simple composite parts. All right, so then I hand over to Malena.
Yeah, thank you. So far, Florian, now he already bridged the gap to the composite area, which I'm responsible for. And you have already seen at the beginning this kind of machine and the video about what the machine is actually doing. And I want to go a bit more in detail on that. Since the beginning actually of composite manufacturing, which was kind of triggered by the aviation industry, costs weren't a big problem. But coming now, as you have seen also by Florian's slides, composites need to face the cost pressure in order to enable more applications in cost-driven sectors such as the automotive sector. And this is why we are focusing since nearly 30 years now, actually more on thermoplastic composite than the usual thermoset composites, which is often used in for example, the aviation industry. And the reason why we focus on thermoplastics is that it has kind of benefits compared to thermoset materials. So this machine, as you've seen it in the video, we built it up several times also for industrial partners. And here on the left, you can see a picture how it currently looks like in our shop floor. And it enables this automated production of composites by this additive production manner. And this machine was set up very scalable. So you can see the tape spools in this picture, and it enables to simultaneously lay several tape spools. So you can adapt it to, let's say, 3 or even 5 tape spools simultaneously. And having this, you can increase the amount of weight which is currently laid, and thus increase the productivity or the output per hour. It also, and this is actually the, let's say, the unique selling point of this thermoplastic tape laying, is that we can decrease the amount of required process steps for the production of parts. And as you can see here, the state of the art, especially with thermoset materials, is that you normally stack the tapes, so you get a laminate, but you need to have a post-consolidation step afterwards in an autoclave. I don't know if you've seen, for example, autoclaves in the aviation industry. They're like very huge, and it's a very expensive step because it takes time and to really cure or consolidate the material at the end. And with thermoplastics and with our technology, we have this kind of in situ consolidation. So this is where the common focus of our groups come together, because we are using, for example, laser heating technologies to locally melt the process zone and then consolidate layer by layer. And hereby, we don't need a further step as, for example, in an autoclave or an infrared oven or something like this. So at the end of this process, we have, for example, a laminate, but also three-dimensional geometries. I come back to that later. For example, composite pressure vessels. And we don't need a further step of post-processing, for example, the consolidation. By having this technology, we are all pretty flexible regarding the material we're using. So this machine can process, for example, very cheap polypropylene tape materials with glass fiber, but can go up to peak carbon fiber aviation grade materials. So this is a nice thing. However, there always with a lot of benefits, there come some drawbacks, and some of this is that the process characterization and optimization is not so easy, because we are locally applying heat in a plastic material, which can cause a lot of effects such as residual stresses, etc., which are thermally induced. So this is kind of the challenge which comes with this new production technology. Well, actually, so it's actually not so new. It came up in the 90s already, but currently, the nice thing is if you can provide with a cost-efficient manufacturing technology, especially the automotive sector gets attention on that technology. So, and what is currently happening, for example, is that it is used this kind of technology for selective reinforcement. Oh, sorry. The selective reinforcement can, for example, be used in the plastics overmolding process. So there are, for example, machine suppliers like Kraus Maffei or Engel, which use this kind of composite inlays, as you can see on the right, and then form it and overmold it by injection molding. And then you have a functionalized composite lightweight part for the automotive sector. So this is already kind of a common technology since 6 or 7 years. I think Florian already showed this kind of door part of Elring Klinger. So this is a very conventional demonstrator of this technology. But the nice thing also with this technology is that you can use it to directly functionalize metal parts. So on the left side, you, for example, see a bumper part or a B-pillar part, which is out of steel, and we have made some microstructuring on the surface of the steel, and by that we can get a kind of a form grip between the plastics material of the tape, which you can see here with the black stripes, and the metal part. So it's had a lot of design freedoms come with this technology. And projects in the last years have shown that you really can increase mechanical characteristics such as the 3-point bending test, etc., and increase the stiffness of the part. The nice thing is that you can also stack the tapes according to your needs. So to this automated manner, we're very flexible also with the fiber orientation. So this means that you at the end have a very load optimized laminate, which you could use in your application. And this is why I'm coming to the next application where we have came up in the last years with a new process chain regarding thermoplastic composites for aviation. And this is the field of fan blades, which I mentioned directly at the beginning of this presentation. So we're currently developing thermoplastic composite fan blades. The reason is that the current, they're actually going back to that slide. So the current state of the art in the manufacturing of composite fan blades is that it's actually pretty manual on the one side. So a conventional methodology is to manually stack the pre-preg layers with the thermoset matrix and then put them into the autoclave. Or there are also some resin transfer molding based methodologies currently on the market or in the application. But what is one of the drawbacks is that it's still not pretty automated, and additionally, thermoset composite materials have a lot of drawbacks regarding sustainability, since the material is not so easy to recycle. And this is why in the last 2 years we came up with a process chain of thermoplastic composite fan blades. Which is made pretty similar to, you can use the machine which we have shown you so far. And then you have the, process chain for the thermoplastic fan blade production looks pretty similar actually to the one of thermoset, but it's also a bit different. And you can already see that also one process step is neglected because we do not need it anymore. So you can see here in the first step is also, for example, by using the machine I've shown you to automatically stack and consolidate the tapes. Then we thermoform it into shape, which is an interesting part because you have to check for the draping behavior, and then you finish it at the end to get the near net shape. And the nice thing here is as well, we can stack or we can create laminates with this in situ consolidation, which has different kind of wall thickness. So we don't have to, we don't create a lot of waste at the end. So this is how the actual process chain looks like, and how we set it up at our facilities. So here you see, for example, the organosheets we have used here, which are heated in an infrared oven and then pressed in the thermoforming step. In this case, we have used as a benchmark conventional organosheets, which you can buy from stock, which have a woven fabric inside. If you use, for example, the tape laying process, we can create these kind of stacks with different wall thicknesses, as I mentioned earlier. And then you wouldn't need as much machining capacity because you have less volume which you have to machine. And here in the lower part, you can see the final manufactured fan blade out of thermoplastics. There are definitely some challenges, for example, thermal challenges in the application at the end. But you can also integrate metal parts into it. As I said earlier, by this combined joining process, this is also possible with thermoplastics. So it gives a lot of potential for future production technologies and applications. However, as I said earlier, there are a lot of challenges in the processing of that locally thermally induced thermoplastic tape placement process. And we are currently integrating the ideas of digital twinning into how to really cope this kind of complexity. And for us, it's very important to digitize really the spatial resolved data. So at the end, when we have a process which is or a laminate which is processed by our machines, we want to see at what area did we have, for example, defects or a quality issue. And we want to locally or spatially localize these kind of process parameters and derive quality indicators, which is, for example, interesting if you want to give your customers a product and then you give like the digital twin of it showing, okay, maybe at that area there has been a defect due to processing or a defect due to materials. And so we have created this kind of automated digital twin, which enables a kind of a post-processing currently of the assessed data and visualize each layer and what kind of process parameters we have at which point. And then we are currently creating models deriving quality indications regarding the final part. Okay, this regarding the automated manufacturing of composite sheet materials. Now I want to come from 2D sheets to three-dimensional products. But before I come to that, I have to shortly explain our initiatives regarding energy storage systems. Because this is also a joint initiative also by Florian's group and mine, and we are very strongly working on future mobility applications. And well, the reason is actually also the growing market on that. As you all know, maybe there is a big German-funded framework of funding more and more initiatives regarding hydrogen and also electromobility. And we really work on that as well. We currently work especially on the case how to upscale your production in these areas, because we see those technologies are kind of have kind of a high technology readiness level itself, but they lack in the upscaling of the production. And this is what we're targeting on. And we see that not only with the automotive sector, we see it with the aviation sector, which is becoming more and more cost driven, and also shipping and commercial vehicles, where we need to face this huge amount of products we need to produce in future. And this is not only, so we have kind of two targets. We're not only focusing on hydrogen or not only focusing on battery cell production, but because at the end, you have to apply the right mobility or energy storage system for the right application. And we have a lot of competencies setting up currently in the area of battery cell production, where Fraunhofer is setting up a big factory, testing factory in Münster, which we are very closely working on, but also in the fuel cell system production, where we see the need for upscaling, which can be seen, for example, on this slide. We see that there's an increasing market of annual sales regarding fuel cell electric vehicles, and we need to face that. And in order to face it, we really need to decrease system costs by in this study, it says 46% in order to get the supply of the systems. And in the case of Florian's and my group, we're especially working on fuel cell, and in that case on fuel cell stacks, and as well as the manufacturing of composite hydrogen tanks. As you can see here on the left side, there's, for example, the manufacturing also with the presses you have seen so far from Florian, how to manufacture these highly accurate bipolar plates for the fuel cell stack. And on the right side, which I want to present you today, the manufacturing of composite vessels. And this is the last use case we're going to present today. So here you can see the machine which is producing with this kind of technology I already introduced for the 2D plates. This machine produces three-dimensional parts, for example, composite pressure vessels. This is a project which focus on the one side on air pressure vessels with around 10 bars of pressure. But we have also a lot of projects currently ongoing regarding the manufacturing of hydrogen pressure vessels, where we need to target 700 or even higher bar pressures. And here you can see also how this is done, because the benefits of thermoplastics, which we are focusing, is the creation at the end of very customized layups. Compared to conventional composite pressure vessel manufacturing technologies, we have a freedom more due to the in situ consolidation. We are enabling load paths which are not yet, were not able in the state of the art or the state of the industry. And here again, due to the complexity of manufacturing, we have also created an automated visualization tool for the digital twinning of composite pressure vessels, which we use, for example, for optimizing our processes and systems as well. This is and this is at the end, maybe to conclude our talk, the very nice thing of our department, or which I really think it's thriving or very motivating, is if you build your own machines or optimize other machines, but if you really are also a system builder or a machine bauer, as it says in Germany, you are also able to get your own code and your source code of your machine, which enables you to really start your digital twin and digitizing efforts at the heart of the machine. So, and this is important if you go to the digitization efforts with respect to process optimization, that you have to know your machine by heart and your source code, etc., in order to really get in online control systems of the machine. And this is what Florian and my group is really doing since a couple of years or decades in that area. So I hope you have enjoyed our talk today, although there were some computer challenges I had to face, and I'm really happy to get in discussion with you now.
Thank you so much, Malena and Florian. So it was not on my side, which I feared the whole time, but it was on your side. That is totally okay, totally fine with me. Thanks so much for the presentation. Very interesting topics. Not necessarily my background, but I see a lot of people here that actually have that background. So typically I start off the question round, but we have a question in the chat, and I'm happy to let Rusty the first question. Somewhere I have that in here, and let me read it out, and you may hopefully be able to answer this question. So Rusty, good to have you here again. When you heat the steel prior to forming, I assume to slam the material to obtain certain tensile properties. If this is the case, does it allow you to lower the base steel material cost?
Yeah, I was thinking about that, but it's more related to my English knowledge. So could you help me out with the word slam?
When you press it.
Ah, okay. Well, so so it's yeah, basically what we can do is by heating up and by quenching the material, we can manipulate the microstructure. So we can, for example, refine the microstructure to give it improved tensile properties. That's a possibility. Usually we aim at, if we already work with high strength steels, we aim at more or less establishing the same microstructure than before, so not changing it too much. But it's certainly a possibility to work on the microstructure by means of the heating, if that answers the question.
I think I wonder.
I guess one part
ahead,
of the
Rusty.
question, yeah, sorry. One part of the question really is, so I understand you're starting with high tensile steel. Can you go with a steel that is a lesser cost, and then as you press to get the micro properties where you want them, does it allow you to use a lower priced steel and still end up with the end properties that you're looking for?
Mm-hmm. Yeah, I think I got the question. Yeah, usually we do the prior that you mentioned. I have no explicit use or example for your question, but I think it should be possible to do that locally. Yes, if it's only a very small section that needs these properties.
Okay, thank you.
You're welcome.
Okay, thank you, Rusties. Anybody else? Any volunteers for questions about lightweight materials, fiber, lasers?
I have some for Malena. I was thinking about the tapes, the thermoplastic tapes, of course, and your focus in that application on the aerospace industry. Are you working with companies like Boeing on that, who manufacture here in South Carolina?
There has been some collaboration in the past, but that was prior to my times. We're actually very kind of focused on the European market. Let's say it's not our fault that we focus so much on the European, but it's just like Airbus is such a strong company in Europe, which is why it's really, really one of the main aviation partners we have here. There are some collaborations indirectly with Fraunhofer and us and Boeing by the University of Twente, where we also have this center in the Netherlands. And there are some collaboration. So Boeing is a very strong collaborator at the University of Twente. And we have this project center at Twente where we sometimes find each other for future collaborations.
Mm-hmm.
Okay. You have more questions then? Otherwise, I can go through my whole lot of list of questions.
Go ahead, Marcel.
I mean, generally, what I saw was, I was thinking the whole time, this is something we need to see, we need to have. The question, of course, always is, when you work with Fraunhofer, is it research, or is it research that is already like commoditization stage or not? So the question is, how far in this process are you licensing? Are you collaborating on projects that are really like putting these things in airplanes or anything, or like just give an overview of how far you are there?
Florian, do you want to start?
Sure.
Or...
Okay. So regarding our heating systems, I think there is currently 2 systems, one in the European and one in the Chinese market. So the technology is now really picking up. So there is more and more requests coming in, and yeah, so we are at the brink of bringing more systems to industrial applications and projects. But it's yeah, I think we have evolved over the years to make our solutions more cost competitive, because that was the biggest hindrance. I think technology wise, it was always our partners were quite satisfied with the technological results, but then we were slightly above the target pricing, and so that's what we've been working on. I think it's picking up.
Well, you pay for the quality.
Yeah, from the composite side is actually, let's say, became in the last couple of years kind of common business to license our technology. So so the machines I've shown you, it's not so actually I think there are like 4 to 5 such machine concepts customized to the client, which are currently in the industry. And there is also a commercialization partner we have for these kind of pre-pro technologies, who licenses this kind of technology from us and brings it to the industry, and as a machine builder, and give things like guarantees, etc., which we as a research institute cannot give, but we can give the licenses to those companies. And there are also some old spin-offs from the 2000s, 2008s, which have this kind of prior technology, which are still which are increasing in the market. So this is actually one of our main initiatives to build new machines and bring it to the industry and license it, so that really the efforts are at the end shown in the industry, but because that's our target, to really show the industrial benefits.
So this sounds as if something that people or manufacturers in the state of South Carolina could heavily benefit. And I mean, I see a lot of application in the manufacturing sector here in the state, so we should keep you on short dial. Then you had this kind of fusion of your both of your topics at towards the end of the presentation, with a focus slide with application, our services, and then markets. About fuel cell together with hydrogen tanks. Like specifically there, how far is that? I mean, this sounded as if it's research, but this is probably highly sought after. So how many years, how many months until people can actually benefit from that?
I think people are benefiting already, but yeah, at very low numbers, right? So with the fuel cells, especially with the fuel cell stack, it's an immense number of parts, because each stack is comprised of like 400 to 500 cells, and these then, for example, for the bipolar plates are like 2 half plates. So you need 1,000 metal parts for one stack, one car. And so that is the challenge to even produce these numbers so that people can use it. I think obviously electromobility has advanced quite a lot in the recent years. So I think hydrogen is still catching up there.
But it's a big topic, right? Further question, if nobody else wants. We
have one from Josh Jones.
Oh, we
in
do.
in terms of, this is for Tobias, it looks like, in terms of forming high strength steels, have you seen significant benefits from using any forming speed control? Servo press.
For sure. There is obviously the issue that that if you increase your forming speeds, your material gets more prone to fractures or any defects. That's something that we also look at if we have a tool at our press, and we try to optimize the curve, how the press moves, with which velocities into the material. But I think that's a second order optimization already.
So you are controlling using speed control for.
Yeah, it can be. Okay. Can be optimized. Yeah.
Josh, any other follow-up? Good.
Yep, thank you.
I have a last question for Malena. Is it possible to conduct trials on the equipment if people ask, like, hey, we want to use that, we want to see if there's any, well, if you can do a trial on it?
Yes, for sure. So this is one of our, let's say, common bilateral industrial projects which we do, and this is also the reason why we have such huge machines, as for example the servo press from Florian, which are very close to or which is a kind of industrial equipment. So this is kind of standard procedure for us, and it's always nice to test new materials or new processes and new targets, for example productivity, on those machines, and optimize them.
Usually that's also the step in adapting a new technology. So a company would come and have their part in mind, and maybe we decide together about a demonstrator geometry and then manufacture and test it. And so they have like something to touch and to show to the management, to make convincing arguments there. And then we can step it up into thinking about the system.
Good. Very last question. Why do you state the model in the very beginning, a model of a car, this is a Q7, Audi Q7, and then putting a Volkswagen Golf as picture next to it?
Sorry?
There was a picture of the Volkswagen Golf,
yes,
and it said Q7 Audi. Audi Q7.
I think Marcel's question is disqualified.
Yeah, I had to ask that.
Okay. Yeah, I think it's the same. It's the same. Basically the same company, right?
Oh.
It's about to show that it's really mass applications that we are targeting.
Very nice. Thank you so much for the presentation. I'm sure there will be follow-ups on this one.
Yes. Thank you everyone for joining us today. We will be sending out the follow-up, sending out the presentation, the video, and information about next month's webinar shortly. Thank you, everyone.
Thank you, everyone.
Thank you.
Thank you for having us.
Especially
have a nice day.
Thank you.
Bye.
Bye.